Today's calculus review topic is how to find arc length using calculus. Arc length would be, I have a curve, but if I straighten it out, how long would it be? The arc length formula is here. In order to use arc length, you must have your curve must be smooth. That means it must be differentiable, and it must be continuous. Of course, if it's not differentiable, it wouldn't be continuous. So it has to be, has to have no cusps, corners, or vertical tangent, or discontinuities. Okay, so this is the arc length formula, and I'm going to show you where it comes from. So you can see that one more time. It's not really essential that you know where it comes from, but I always like to think about that. So one huge idea in calculus is I have something I can't figure out, so I'm going to cut it up into infinitely many pieces, or I'm going to make a little tiny cut and examine that tiny cut, because in that tiny region I can pretend my function is linear. And so that's what we do with arc length. We say, well, this is a curve, but if I zoom in and just look at a little tiny region, I can pretend it's linear. So that's the first step in arc length. And if I do that, I can draw a right triangle that connects 2 points on my curve. And I can pretend, if my points are close enough together, that the hypotenuse would be the length of the curve. The height of that triangle would be the change in y, and the base of the triangle would be the change in x. And since it's a right triangle, we can say that the change in x squared plus the change in y squared would be the length squared. I'm going to do a little manipulation at this point, just to kind of see where this arc length formula comes from. I notice that the arc length formula has a derivative in it, and I know that derivative is dy over dx. So at this point, I'm just going to divide everything by delta x squared. If I do that, I get 1 plus delta y over delta x squared is equal to the length squared times delta x squared. And now the magic of calculus is this isn't exactly true. The length is not really a dot to dot. Like, I can't really cut this into straight lines. But if I make my cuts infinitely small, if I make them so tiny that there are infinitely many of them, then I can do it. And I do that with the magic of limits and with the magic of integrals. So instead of saying the words delta x and delta y, I'm going to use the magical infinitely small dy and dx. I'm going to put this in parentheses. Actually, I'm going to do this even better. Now, I want the length, so I'm going to solve for L here. So I'll take the square root of both sides of this equation. So I get the square root of 1 plus dy dx squared is equal to L over dx. All of these are positive measures because we are dealing with length here. And then if I want to solve for L, I would have to multiply both sides by dx. So I get the length of one of these little tiny slices is the square root of 1 plus dy dx squared times dx. But I don't want one tiny little slice. I want the length of the whole curve. And that's what the magic of the integral does for us. So to add up all of these little tiny pieces, then I would use an integral to add all of those pieces, infinitely many pieces together. And it's kind of nice how it works out so that there's a dx there. Okay. So that's arc length. Today's AP problems will give you a chance to practice arc length. And it's rare for arc length to be a non-calculator question, but also this AP test is all calculator. So don't worry too much about trying to integrate by hand, but you will have to take derivatives when you're doing arc length. So you fill the derivative into that formula. All right, good luck today.